Hello, everyone. Hello, Jonathan. It's a great pleasure to present at the Cambridge Particle Meeting for the first time. So today I'm going to talk to you about the volume fraction of soot, one of the most critical characteristics in combustion. You can hear me now again, right?
Yes.
Okay, good. So it is one of the most critical characteristics in combustion, as it is essential to close the soot mass balance. And closing the soot mass balance is actually not an easy challenge. Just a moment. Okay. So, for example, here you can see the soot volume fraction that has been obtained only from mobility size distribution data in a premixed ethylene flame. So this volume fraction is up to 20 times larger than the volume fractions obtained by combustion models published back in 2003. Originally, this discrepancy was attributed to assumptions made regarding the particle dynamics or the reaction kinetics in these models. However, as you can see over here, the same soot volume fractions obtained from the same mobility size distributions are still between 2 to 10 times larger than those obtained by more complex combustion models that were published last year. So in order to better understand the origin of this problem, let's focus next in this benchmark premixed ethylene flame that has an equivalence ratio of 2.07. So here, in the y-axis, I'm presenting you the soot volume fraction obtained as a function of the height above the burner by coupling mobility size distribution data with an aerosol particle mass analyzer. So this is probably the most accurate method to get the soot volume fraction, as we can monitor accurately both the number density of soot as well as the particle volume. However, the soot volume fractions that are available using this method are rather limited. As you can see over here, we have the volume fractions only for 2 heights above the burner. So more commonly, the soot volume fraction is obtained only using mobility size distribution data and assuming spheres. So in other words, the fractal-like morphology of soot is neglected. And this, as you can see, results in an overestimation of the real soot volume fraction up to a factor of 4. So this overestimation is on par with the discrepancy that I showed you in my previous slide, the discrepancy between combustion models and data. So in our recent publication in the Proceedings of the Combustion Institute, we derived this new relation for the soot volume fraction that accounts for the evolving soot morphology. So how we go from spheres to fractal-like aggregates and agglomerates. So the volume fractions that we obtained using mobility size distribution data together with this volume fraction relation were in excellent agreement with the volume fractions obtained directly by an aerosol particle mass analyzer. Now, I would like to mention here that this kind of spherical assumptions are not only used in aerosol diagnostics, but also in laser diagnostics. So here, I'm presenting you the soot volume fraction measured as a function of the height above the burner in a premixed ethylene flame with an equivalence ratio of about 2.3. And these volume fractions are measured by light extinction. In other words, we obtain the soot volume fraction by dividing the absorption coefficient by the absorption function of soot, which evolves as a function of the height above the burner based on the soot morphology and composition. However, the soot volume fraction is commonly obtained using a light extinction data with a constant absorption function with a constant absorption function that has been derived for spheres with a constant composition. So actually, in our recent publication, we obtained the soot volume fraction using the same light extinction data, but with a variable absorption function that accounts for the evolving soot morphology and composition. So the volume fractions that we derived this way, you can see over here that they are up to 2 times smaller than those obtained for spheres, neglecting the realistic soot morphology and composition. Now, so far, we had focused on premixed flames. But I would like to mention here, to highlight here, that it is challenging for combustion models to close the mass balance also in diffusion flames, such as the well-known co-flow diffusion ethylene flame that was introduced by Santoro and co-workers. For example, here you can see the soot volume fraction that has been measured at the center line of the Santoro flame by light extinction. You can see that these volume fractions are between 8 to 17 times larger than those obtained by different combustion models that were published just earlier this year. Similarly, at the maximum volume fraction path of this Santoro diffusion flame, you can see that again, the volume fractions obtained by light extinction data are up to 2 times larger than those obtained by these combustion models. So this motivated us to better understand, to verify the accuracy of these light extinction measurements in the Santoro diffusion flame. For this reason, I'm presenting you here the soot volume fraction measured as a function of the height above the burner at the maximum volume fraction path of the Santoro flame using thermocouple particle densitometry. And here you can see the soot volume fraction obtained by light extinction using a constant absorption function of 0.16 that has been derived for spheres with a constant composition. So here you can see that actually the volume fractions obtained from light extinction data, assuming spheres, are up to 4 times larger than those obtained by thermocouple particle densitometry. Again, remember that this overestimation is on par with the discrepancy between combustion models and light extinction data that I showed you before. And we can see a similar trend at the center line of the Santoro diffusion flame. So here you can see the soot volume fraction measured as a function of the height above the burner at the center line of the Santoro diffusion flame by microscopy, as well as by light extinction, again for spheres using the same absorption function that I showed you before. So again, these light extinction measurements overestimate the soot volume fraction by a factor of 2. So clearly, we need to improve the accuracy of light extinction measurements in order to assist combustion models to close their mass balance. In order to do this, we used our discrete element model that we have presented in previous combustion conferences, as well as yesterday at the ETH nanoparticle conference. So I will go briefly through the description of this model, but feel free to ask me any question right after. So we have a simulation box that we fill with monodispersed nanoparticles having an initial mobility diameter of 2 nanometers. Then we follow the particle motion and coagulation in detail inside this simulation box as a function of the residence time. Most importantly, we account for surface growth of the soot nanoparticles by the hydrogen abstraction and carbon addition mechanism. So we estimate how many acetylene molecules react with the soot surface based on the respective reaction kinetics and collision dynamics. Then we increase the soot primary particle diameter by applying this mass balance for every acetylene molecule. So using this discrete element model, we generated simulated soot aggregates and agglomerates that have identical number of primary particles and average primary particle diameter with those measured by microscopy at different heights above the burner. So firstly, we would like to validate the morphology of our simulated soot agglomerates. In order to do this, we used the light scattering data of the soot gyration diameter obtained as a function of the height above the burner at the maximum volume fraction path of the Santoro flame. We have 2 different light scattering datasets over here. The original one from Puri et al., published back in 1993, and the one from Zhang and Thompson, published in 2016. And here you can see the evolution of the diameter of gyration obtained from our simulated soot agglomerates. You can see the small soot aggregates formed at small heights above the burner rapidly grow, mostly by agglomeration, but also surface growth, and they reach a maximum at about 5 centimeters height above the burner. Then oxidation takes over and decreases their diameter of gyration. So as you can see over here, the diameters of gyration that we obtained with our discrete element model are in excellent agreement with those obtained by two different light scattering datasets. So this validates the morphology of soot simulated by our discrete element model. So we used these realistic but simulated soot agglomerates as an input to discrete dipole approximation simulations. That way, we are able to obtain the variation of the soot absorption function in terms of the evolving soot morphology at the maximum volume fraction path of the Santoro diffusion flame. So here we divide essentially the absorption coefficient of soot agglomerates obtained by discrete dipole approximation by the volume equivalent diameter of these agglomerates. So we go back to the soot volume fraction evolution at the maximum volume fraction path that I showed you earlier. We are going to use exactly the same light extinction dataset that I showed you before. But now we are using a variable absorption function to account for the evolving soot morphology. As you can see over here, the soot volume fraction that we obtain that way is in excellent agreement with the volume fraction obtained by thermocouple particle densitometry. So just accounting for the realistic soot morphology improves significantly the accuracy of the soot volume fraction obtained in the maximum volume fraction path of the Santoro flame. So we also looked into the evolution of the soot volume fraction at the center line of the diffusion flame. Here, though, please notice that at small heights above the burner, we have the formation of young soot aggregates that also contain significant amounts of organic carbon. Of course, as we go up in the flame, the young soot aggregates gradually mature, and the organic carbon is gradually oxidized. So in order to account for the evolving soot maturity and organic carbon content, we used the refractive index relation that I presented yesterday at the ETH nanoparticle conference and we recently published in Carbon. Using this relation, together with the simulated soot agglomerates, we are able to account for the evolving soot morphology, maturity, and organic carbon content. So the variable absorption function that we obtained this way results in soot volume fractions that are in excellent agreement with the volume fractions obtained by microscopy. So with our method, we are able to monitor accurately the soot volume fraction, both at the maximum volume fraction path, but also at the center line of the diffusion flame. With this, I would like to come to the conclusions of this work. So we simulated the dynamics of soot morphology and light absorption in the Santoro diffusion flame by interfacing discrete element modeling with discrete dipole approximation. Firstly, we validated the soot morphology obtained by discrete element modeling with light scattering measurements. In particular, as you can see again over here, the evolution of the soot gyration diameter obtained by discrete element modeling as a function of the height above the burner was in excellent agreement with the gyration diameters obtained by two different light scattering datasets. So we used these simulated but realistic soot agglomerates as an input to discrete dipole approximation simulations in order to obtain the variation of the absorption function in terms of the height above the burner. Using this variable absorption function, together with light extinction data, we were able to obtain very accurately the evolution of the soot volume fraction at the maximum volume fraction path, as well as at the center line of the Santoro diffusion flame. And the volume fractions that we derived that way were in excellent agreement with data from thermocouple particle densitometry, as well as with microscopy. Furthermore, we showed that neglecting the realistic soot morphology and composition resulted in an overestimation of the soot volume fraction by light extinction by a factor of 2 to 4. So I would like to remind you that again, this overestimation is rather large, and it is on par with the discrepancy observed, shown in the beginning of my presentation, between combustion models and light extinction measurements. So the method that I presented you over here can be used in tandem with laser diagnostics to monitor accurately the soot volume fraction in diffusion flames and assist combustion models to close their mass balance. With this, I would like to thank you for listening, and I will be very happy to answer all your questions.
Thank you very much indeed, Georgios. Again, it's a very impressive agreement between the experiment and theory when you've done your corrections. That was very good. Okay, so questions are coming in. We've got a question from KP Geigel, who's asking, along the center line, you already start with aggregates. What precedes this stage?
So typically, before the aggregate formation, we go all the way from inception to surface reactions, aggregation, and agglomeration. At the center line, though, essentially, we have rather low temperature range where essentially the maturation of soot is rather delayed. It's not like in the maximum volume fraction path where the soot agglomerates mature very fast. So at the center line, let me go back. Before this, we have rather spherical soot nanoparticles that contain even more organic carbon content. They grow by surface reactions, aggregation. At the same time, the organic carbon content is gradually oxidized, and we reach this stage over here. Does this answer the question?
I hope so. Okay.
If not, you can send me a message and I can reply again.
Absolutely. So we've got two questions from Jeremy Yon. There is no hypothesis of spherical particles when interpreting light extinction with RDG approach. Perhaps using E equals 0.16 is not really adapted to soot.
I didn't get the first part. What did he say exactly? Hysterical hypothesis, or?
Jeremy, are you there to
yes,
clarify that?
Yeah,
we can hear you. Yep.
That's it. It's just a remark concerning the first part of the presentation. For me, when we interpret light scattering or extinction, most of the time, if we measure volume fraction based on extinction measurement, there is no hypothesis of spherical particles, especially if we consider RDG.
Jerome, thanks for the clarification. When I say that a spherical assumption is used, refers to how this 0.16 value has been derived. So if you check the paper of Puri and co-workers published in 1993, essentially they matched their light scattering measurements, their light extinction measurements with their light scattering measurements, assuming spheres using a spherical model. Okay, and this led to this value of 0.16 that they proposed in their publication. Is it clearer now?
No, to me, we can compare with most recent analysis, experimental analysis, because since a long time we don't consider a spherical approach. I
can show you over here. For example, the evolution of the absorption function. Okay, in the right axis, the red axis. Of in the left, I'm showing it to you at the maximum volume fraction path, and here at the center line. At the maximum volume fraction path, the soot nanoparticle agglomerates are already mature. So they have already an absorption function which is close to 0.4. It's in excellent agreement with the one measured by light extinction, and it is also in good agreement with what has been measured recently by Ryle-Debye-Ganz theory, which I guess is the one that you are referring to, right?
Yes, yes.
Excellent. And this is, of course, working very well for the maximum volume fraction path. Now, when we are looking at the center line, of course, here we have young soot that contains of organic carbon. So here you can see that the absorption function actually evolves as a function of the height above the burner. Okay, so we only reach the absorption function, the asymptotic one for mature soot of 0.4 for heights above the burner that are larger than 6 centimeters. Is it clear now, Jerome?
Yes, yes, yes.
Okay.